Good afternoon, everyone. We will start in class in 1 to 2 minutes time. To answer that question regarding quiz 2 and quiz 3, you guys will get some advance notice on when we'll be doing those in particular. For now, what I can tell you is that quiz 2 is most likely going to be next week, but if that changes, I'll let you guys know on the forum. Quiz 3 may be way later down in the semester, but like I said, you will get advance notice when these quizzes are coming out. Alright, good afternoon everyone, and today's session we're going to be finishing up our sorting and searching algorithms lecture that was the last lecture from last week, and then we'll be moving on to the start of our data structures overall topic, and in particular we'll be revisiting stacks and queues, which was a topic that we did in year 1 programming, as well as linked lists, and we're going to see how each one of these operate in particular. Now, the concepts behind these data structures, they're very easy to understand, and the implementations of them are also very easy because they have very simple operations. But as we move on to advanced data structures later on, you're going to see why these structures that we do here, which are considered simple data structures, how they build with each other to form these advanced data structures. So let's get started with our second sorting and searching algorithms lecture for today. And we saw that last week, the 3 algorithms that we did was the insertion sort, the selection sort, and the bubble sort. And in today's lecture, we're going to be doing the other 3 algorithms, which is going to be merge sort, quick sort, and bucket sort. We'll also look at one searching algorithm in particular, which tends to be very popular when it comes to programming interviews, which is going to be the binary search algorithm. And you have already seen this binary search algorithm in action in a previous lecture, where we saw that we could start off with an entire array, and then in order to find a particular value in the array once it was sorted, we just kept on dividing the array in half and searching each halves accordingly until we found that value. So merge sort is basically a divide and conquer technique where it tries to figure out how fast we can go about dividing the entire problem into subproblems, and then we can just sort each subproblem and then combine the result all together. It is one of the more popular sorting algorithms that you would see. The worst case time complexity is O(n) log n, which is not bad in comparison to our previous 3 sorting algorithms, where we had a complexity of O(n) squared, which was kind of horrible in comparison to this. And then you're going to see that most of these algorithms here are going to end up being a little more optimized than the previous 3 sorting algorithms, and some of these can actually be applied to large data as of such. So Midsource starts where you divide the array into equal halves, and then you start combining them in a sorted manner because you start sorting each one of these halves in. So the visual example here is that if we start with this unsorted array, and then we divide this array in half, so we have the first 4 elements as its own subarray, and then the next 4 elements as the next subarray. We keep on doing these divisions accordingly for each half as we keep on going. So instead of having 2 groups of 4, we now have 4 groups of 2. And then we keep on going until we get to only groupings of 1. And these groupings of 1 are referred to as an atomic element, where the definition of the atomic element meaning that is that there's only 1 unit that can be associated with it. So this 1 unit here is going to be 1 piece of the entire data array that we started with. So then, after we do all these divisions, we combine them in the same manner that we broke it down, and then we go about doing the comparisons here to figure out how do we go about sorting the entire thing all together. So we're going to see how this sorting and combining is done that forms our merge sort algorithm here visually. So we start with 14 and 33, which was our first 2 values that we had. And we see, okay, is 14 and 33, which one is the less value and which one is the greater value. And we put the less than values on the left hand side and the greater than values on the right hand side in particular. So in this case, 14 and 33 is already sorted. 27 and 10 are then compared, and then you realize, okay, 27 is greater than 10, so these two have to swap accordingly. The 35 and 19, the same thing happens, these two have to swap, and 42 and 44 is already in order. So once all these swaps here happen accordingly, for each pair of values, this will be the end of our first iteration for our merge sort. So the result here will end up looking like this. But each pair of values is sorted from the least most value to the greatest most value. So this is where we sorted values in pairs. For the second iteration, we're going to be sorting values by 4s instead. So we group the first 4 elements here, which have been already sorted to begin with. And then we group the other 4 elements here. And then we sort them accordingly to see, okay, which values here are supposed to be in order accordingly, the same way as if we were doing the sorting for our first 2 values. So once these elements here are compared accordingly, as of such, and they're sorted again, this will be the end of the second iteration where each grouping of 4 elements is going to be sorted from lowest most value to greatest most value. So you'll see here, this 10 will be the least most value, then the next following value will be 14, 27 here, and 33. Similarly, 19 will go here, then 35, then 42, and 44. An event if the array is an odd number length, it will be such that the groupings will end up being somewhat different in nature. So you will end up getting a grouping where you will end up having 3 elements as of such. And instead of like you trying to group in terms of 2, 2, 2, and 3, some cases you may want to change the groupings so that you get like an even split. But if you can't get an even split accordingly down to some minute number, they go about doing the sorts and as a result, so they'll have like 2, 2, 2, and 1. So they'll sort all the pairs, and then when they sort all the pairs, they look for the least most value in every one of the pairs, and then they compare it to the odd value that stands out, and they'll figure out, okay, where does this odd value supposed to be placed accordingly, and once they figure out where to place it, then they go about grouping accordingly and keep on going up in order until they finish the entire sorting. So that odd element that's going to be out of grouping is introduced in a separate way to go about sorting it accordingly with the other grouping. So once we group it in terms of 4 and we sort in terms of 4, this will be the end of the second iteration. And then the third iteration, we compare the elements into groups of 8 here. And then once they're sorted accordingly, we merge them into the final array as of sort. And the end result here will be the sorted array that we require for merge sort. So merge sort is kind of like similar to your bubble sort that you saw earlier, where it does the swaps accordingly. Same thing like if you've seen like the selection sort where we had the swaps. But instead of operating on the entire array, it breaks it down into sub-arrays. And it tries to group it in terms of pairs. If the array is odd in length, it will have an odd value that will stand up by itself, and it will do the sorting for the pairs accordingly, and then do a comparison of the odd value to see where it actually can lie, and it will keep on doing the sorting as of such. So this is basically the general algorithm for merge sort. And basically it just keeps on dividing the array recursively into 2 halves until it can no longer be divided, and it just sorts each half accordingly and then rebuilds the array accordingly for the sorted version that is required. The code for merge sort is actually provided on my learning, so I suggest that you guys download it and analyze it and see how it operates. And yes, it can work for odd values of the array length as well, so you can actually see how it operates step by step. Alright, any further questions on merge sort? Alright, doesn't seem like we have any further questions on merge sort. Alright, let's go on to our next sorting algorithm. So, quick sort is also a very popular sorting algorithm that you tend to see already have existing implementations in its own programming libraries for C++, Java, and other programming languages. And it's basically based on the same idea of the merge sort, but it operates a little bit differently, and we're going to see how it operates differently as a result. Okay, so before I move on, merge sort basically, instead of operating on the entire array, it breaks the array into subparts, and it sorts each subpart and then reforms the array. The other sorting techniques that we learned operates on the entire array, and it does not break it apart at all. Alright, so we're going to see how quick sort here is going to be a little bit different from our merge sort in a bit when we start watching visually. So quick sort, what it does here is that it uses something that we refer to as a pivot. And the pivot is going to be, how do we figure out what's going to be technically on midpoint of our subarrays. And everything less than the pivot will go onto the left hand side, and everything greater than the pivot is going to be onto the right hand side. And quick sort, because it uses this pivot value here, it's a little bit different than Midsource because yes, it does break the array into two subarrays, using this pivot value to know where to break the array accordingly. But at the same time, the left-hand side and the right-hand side do not have to be equal in length, depending on the value of pivot that is used. Now, quicksort is also very effective for large-size datasets, because depending on the pivot value, it may be such that you may not need an entire section of data, and you can optimize which part of the data you wish to sort in particular, using a specified pivot value to divide your data accordingly. The average and worst complexity, however, is going to be ON squared, which is a little bit horrible, but depending on the value of pivot, it actually can improve quite dramatically. So there's an animated visual effect here indicating the steps of how quicksort operates. And you can see here that it selects a pivot value and it starts doing the comparisons around the pivot value in order to figure out, okay, which value is less than pivot, which value is greater than pivot. And it does the swaps accordingly to make sure that it knows how to go about doing these pivots. Once it figures out that it does all the swaps, it then puts the pivot value accordingly where it needs to be. So you can see here that 31, 35 is less than, and 26 was less than, so it puts everything that's less than the pivot on the left hand side, and everything that's greater on the pivot on the right hand side. It also does this by comparing pairs of values starting from the outermost into the innermost. So it started with these two, then these two, and then it compares these two accordingly as it keeps on going. And then it figures ways to insert the pivot after it does all the insertions accordingly. So for your homework here, and you know why, at this point, why I give you guys some homework, is to try to examine the animation and figure out how it works. And you also have the code provided to you on my Learning for Quicksort, so try to see how does it match back up to the code in particular. The general algorithm for quicksort is given to you guys here, which basically is going to match up to the code implementation that is provided on my Learn. Alright. Now, if there are any particular questions on quicksort, normally I would entertain them here in the chat, but because I'm giving you guys some homework, questions for quicksort will be entertained on the forum once you start attempting this to understand how it operates. But once you basically analyze the algorithm here, you'll have a good idea of how the animation matches back to the algorithm. Bucket sorts is also another popular algorithm that is used for sorting, and this is also referred to as the scatter-gather approach. And we'll see visually why it's going to be the scatter-gather approach in a little bit. And the reason why it's called bucket sort is that you'll see that these buckets here kind of operate similar to that of a histogram, where once the values lie within a certain range, it gets sorted into that particular bucket that specifies that range. And once these values are put into each bucket within the range, each bucket can be sorted using any particular sorting algorithm, because in particular, the values that's going to be inside each bucket, the amount of them is going to be small in nature. So you can choose any sorting algorithm to sort the contents of the bucket as required. If you wish, you can use the same algorithm for sorting each bucket for the entire algorithm, for the entire bucket sort in particular, sorry. And this is incredibly useful when you have extremely large data and it cannot fit in your available memory. You can go about sorting these in chunks one by one and then putting them back in order as a result. So it comes like if you're doing bucket sorts here, bucket sort is extremely effective for when you have limited memory and your data set is very huge and it cannot fit in your available. The best time complexity for a bucket sort is linear, which is going to be O of n plus k. I want you guys to figure out what the n is going to be here and what the k is going to be here in the next few slides. And that's also going to be part of your homework, to try and figure out what does the n represent and what the k represents for our bucket sort algorithm. So in the best case, you'll have a linear order algorithm, which is going to be O of n plus k. In your average case, you will have O of n. And in the worst possible case, which rarely occurs, you'll have O of n squared. So we're going to see two examples here that illustrate bucket sort, and let's see which one actually is better explained for you guys as a result. So remember, bucket sort here is the scatter-gather approach. So we start our initial array here with all our values, and we scatter it accordingly, such that each one of these buckets here represent the range of values that we want these values here in the initial array to be sorted into each bucket. So our first bucket here can only hold values between 0 and 5. So in this entire array, only 1 can go here. Second bucket can hold values between 5 and 10. So we see that it's going to be 9 and 8, and so forth for 10 and 15, 15 and 20, 20 and 25. Once we scatter the array here into its range buckets accordingly, we then swap the contents of the buckets to make sure that the contents of the buckets here are in order. Similar to the approach that was used for our merge sorts that we saw earlier on. But the contents of each bucket here is sorted. And once the contents here are sorted, we then go from the lowest range to the highest range in order and rearrange it so that we gather the values and put it back into order as required. The step-by-step example here is going to give us the in-depth explanation as to what actually occurs with each one of these operations. So if we have an unsorted array here, which is going to be 7 values in total, typically we can say, okay, these are some values here, but we want to create an array here of size 10, and each individual slot in the array here is going to be used as a bucket for storing elements. So we're going to be inserting elements into each one of these buckets here, which are going to be slots in the array, starting with left to right here in order to get these values going in. So we can, depending on the range that we have here, we can specify what range is going to be for each individual slot in the array. So we can be like, okay, this goes from 0 to 0.1, this can go from 0.1 to 0.2, this go here from 0.2 to 0.3, and so forth as we keep on going. And we can sort these values here accordingly into each one of these individual slots in the array. Once each of these elements are slotted into the buckets here, or each slot in the array, representing the range, the same thing happens as we saw in the high-level example. We sort the values for each slot using a sorting algorithm, and then we just offload each of the buckets in turn to form our finalized sorted array. So you see here, 0.23, 0.25, then 0.32 goes here, 0.42, 0.47, 0.51, and 0.52. The general algorithm for bucket sorts is given here, and the code for bucket sort is also provided on my list. Alright. Any particular questions regarding the bucket sort algorithm? Ask now. Yes, so depending on the data that's going to be processed in each one of those buckets, you choose a suitable sorting algorithm to sort each bucket accordingly. And that choice can actually be dependent on the nature of the data or how many values are going to be inside each bucket and so forth. So to sort the contents of each bucket, the suitable sorting algorithm to use, you can just choose which one in particular that you want to use based on these criteria. Sorting is not only used for arrays. What we're going to see is that when we move on to our data structures, there's also a way for you to use sorting for these particular data structures as of such. But the reason why we use arrays for explanation is that what you're going to quickly realize is that most of these simple and advanced data structures are basically just fancified versions of your simple array in just some different form or fashion. So once you understand how it operates for one array, it operates for all arrays. Close enough with the O of n plus k, but the explanation needs a little more work. So, as I say, think about it a little bit more, and there's a reason why I'm giving you that for homework. So, you got the n part correct. The k part is what you have to think about a little bit more. Right, it doesn't seem like we have any further questions on bucket sorting. Right, let's go on to our search algorithm, which we actually do have a little bit of experience on so far. So we actually seen this binary search algorithm in practice, and in particular we saw it in our complexity lectures. And we're going to be talking about it here in a little bit of detail, so we can get a better understanding of how it actually works. So binary search is also a divide and conquer approach that we go about doing. And it's also one of the most popular search algorithms that is used in industry because of its nature and how fast it actually can operate in particular. The next loop for sorting, yes and no for answering the bucket sort approach, but like I said, think about it a little bit more. And if you got any further questions regarding that, I'll answer it after once I finish each for today. So the average and worst time case complexity of binary search is O of log n, and we saw in particular that when we did the analysis of this in our space and time complexity lectures, that log n approach was where we had a constant division by some sort of factor. So that's why we end up getting this order complexity here for binary search as a result. And the keyword here being binary is that binary only can take two values. It's going to be 0 or 1. And because of its only two values, that means we'll always be dividing by halves as we keep on going throughout our entire search. Now, before binary search can actually be done, your array needs to be sorted either from lowest to highest or highest to lowest. And then you can actually do your binary search effectively. If the array is unsorted, the binary search is going to take extremely long. And as a result, you may end up getting wrong results accordingly, or that you just end up taking like 3 or 4 times the amount of time just to try and find a particular value because it's going to be obscured in some form or fashion somewhere. So remember that binary search can only operate once the array has been sorted either from lowest to highest or highest to lowest. So in our particular example here, we have a lowest to highest sort. And let's say we're searching for the value of 4 here in particular. And doing binary search, you need to set 2 pointers for the lowest most value and the highest most value as a result. We then find the middle value from the lowest and the highest by observing the positions here and the length of the array. If x here is designated as the value that we are searching for, if it's equal to the middle here, we return that value and basically we stop searching because we found a match. If it's such that the search value here is greater than the mid value, we search on the right hand side, and if it's going to be lower than the mid value, we search on the left hand side. So in the event where our search value here being x is greater than the mid value, we're going to be comparing x here with the middle element of the right hand side of mid. And as a result for this particular case, we had our, I think I'm going to have to correct this, our lowest most value here, no, this is correct, sorry. So we go about setting this so that my low here is going to be mid here plus 1. So that way we're only searching on this side here. So when we do this, in particular, I'm going to annotate a little bit. The original low was here, but this is going to move to here instead. And this pointer here will still remain high. So we only be searching here accordingly as a result. If it was that, in the event that our x value here was lower than the middle value, we need to move the high pointer that originally existed here to match to the lower half accordingly for our search range. So just to re-annotate, what this does is that originally we had high here, but then when we do this, we move high here to this point, which is less than our mid value, indicating the range of values that we need to search for as a result. So in moving the low and high pointers here, we reduce our search range accordingly each time. And in the reduction of the search range that we keep on doing, we end up doing this until we actually find our value as a result. And eventually, we will end up finding the value that we search for. So there are two ways to go about implementing binary search. There is an iteration algorithm, which is highly effective, and it's a simpler one to learn. But there's also a recursive algorithm that is preferred in certain cases. So in your programming interviews, typically you can choose one or the other because they'll just ask you how you go about doing a particular implementation of it. But it also is very helpful to know both implementations, because there may be in a case where they say, okay, for this particular application, we need to use a recursive implementation of the binary search. Or for this particular implementation, we need to use the iteration version of it. But it's very helpful to know both versions because they can be advantageous in certain situations. So the code for both the iterative and recursive binary search algorithms are provided on my learning, so you can actually see how it matches back to the algorithms that were formulated here on the slides. And just concluding regarding our sorting and searching algorithms lectures, we need to know when to use which particular sorting algorithm for different types of situations, depending on the size of the array, how much data we're operating with, how much memory we have available, and so forth. And we know each sorting algorithm has its advantages and disadvantages in certain types of situations. Searching algorithms can only operate on data once this data has been sorted from lowest to highest or highest to lowest. And the most used sorting algorithm, the most used searching algorithm that is popularly used and is one of the easiest ones to implement is the binary search algorithm. And we saw here that binary search keeps on reducing the search range each time when it does not find a match. So it does the search on the left hand side and the right hand side accordingly and keeps on repeating the steps until we find that match, effectively dividing our datasets by half each time until a match is found. Alright, so are there any particular questions regarding the contents of this lecture at this point? So this brings us to the end of a sorted and searching algorithms lecture and topic. Alright, doesn't seem like there are any questions. So in addressing the last question there, remember N and K here are going to be different lengths of different things regarding your bucket sorts algorithm. So you had the idea where N is going to be a static length, N is going to be the length of the entire array that you start with, but K also needs to be the length of something else, and that's going to be the maximum length of any particular bucket, which is compared across the lengths of all the buckets in. So that's why you end up getting O of N plus K as a result. So yes, you had the idea with the loops, how it goes about doing that. Remember, you need to also define what N is and what K is with respect to data sizes in order to finalize your full explanation. Alright, let's move on to our data structures topic in particular. Close this off, I'm keeping my ink annotations here. Alright. So the first set of simple data structures that we're going to be revisiting here is known as stacks and queues, and you may have actually been introduced to this in your year 1 programming course, but we're going to go through a quick recap of how these operate. In particular, we don't need to go through any particular operations regarding this. All the code is provided for you on Island regarding how stacks and queues work. And it's just basically, once we understand how it operates, we go about just analyzing how it operates with respect to how we write the code accordingly. Yeah, you probably typed it wrong, but once you have the general idea, it's okay. It's just a matter of knowing how to go about explaining the idea properly. But that's not a problem. There's a practice makes perfect, and eventually, once you keep on practicing, you'll have the idea on how to explain it properly and so forth. So, not a problem. We're here to learn. Just make sure you make your mistakes now, because when it goes into the working world, mistakes can be quite costly. So it's better you make your mistakes now in the classroom. Alright, so yeah, as I'm saying, we're going to be revisiting stacks and queues here, and we're just going to see how they operate, and the code for them actually is quite simple. Regards to how they do operate, so we don't have to go through in extreme detail as to how each one of these works. So stacks use what we refer to as the LIFO principle, which is last in, first out. And it's such that the last item that was inserted on the stack is going to be the first one that is going to be deleted from it. And in some cases, there may be instances where you may want to end up using a stack instead of an array. And I'm going to leave you guys to figure out which particular instances you may want to do this. A good hint will be that maybe you want to think about data caching and the order in which data can be cached and how it's supposed to be released. And stacks, because it uses that last in, first out principle, there's a few restrictions on insertion and deletion of elements, and how you can view particular elements within the stack itself. So for insertion and deletion, it comes like the only thing you can access is at the top of the stack. And if you need to get to a particular value later on within the stack, you're going to have to keep on removing elements from the stack until you get to it as a result. Stacks can also be implemented recursively, and that's typically the general implementation that is used for any particular stack. It's rare to kind of see an iterative stack, but they do exist accordingly. But in any general implementation for a stack, you tend to see most of the times it's going to be some sort of recursive. So in using a particular stack, each time when you need to insert an element, if this was the original data that was already in our stack here, and visual sakes, it's vertically assembled here, when we need to put a value of 4 here, it comes like we place that value of 4 on top of all of the existing data as a result. But if we need to get to a value of 2 here, we have to remove 4 and then 1, and then we can get to the value of 2 as a result. So stacks can operate like a mailbox that only has an opening on the top, or basically like any box where the opening is only at the top, and you can only access the top element and see what the top element is as a result, and you can't see any of the remaining elements until you just keep on removing the top elements to get access to that in particular. So there are general operations for any stack that always need to be implemented. The push and pop methods are the most basic ones that you need to do, which is going to be to add and remove items from the top of the stack. Print can display the contents of the stack accordingly, so it can actually go through the entire stack and tell you what the contents are. But it means that it cannot access the contents in random order. It can only access the contents from the top elements. Top element or peak will just return whatever element is at the top of the stack. Number of items can tell you how many elements are in the stack. Full and empty will tell you if the stack is full or if the stack is empty, just by the namesakes of them. Typically, you can use a class implementation for any particular stack, and this class implementation of the stack, I think, is provided to you on MyLearning as well. You can actually have a look at it and see how it actually operates. And you can actually see the code for each one of these in particular. Alright. Any particular questions on the operation of stacks? Oh, they're not both created. It's just depending in certain implementations, people either use the top element or peak as the name of the function. It's the same function, just different names for them. So you may end up seeing like different implementation of the stack, and instead of seeing a top element function, you'll end up seeing a peak function. But it's the same thing, it's just different names. Alright, doesn't seem like we have any particular questions on stacks, so let's move on to queues. So queues here use what we refer to as the FIFO principle, which is the first in, first out. So the first element that is added in the queue is always going to be the first element to be removed as a result. So a queue basically represents a physical line, like if you line up in the bank or line up anywhere in particular to a cashier. The first person who is there is the first person to get served as a result, and then once they're finished, the next person in line moves forward and so forth as we keep. So any new elements that are to be added to the queue is always added at the end of the queue or at the back of the queue, and elements that are to be removed will be at the top or the front of the queue. Queues can also be implemented using a linked list structure, which we're going to see in our next in our next lecture, what actually is a linked list. We actually did this in year one programming, so we're also going to revisit it as well. So queues here, such that if we say this is the front of the queue here and this is the rear of the queue, is that the 9 value here was the first value that was inserted into the queue, then followed by 5, 7, and then 3. If we insert another value into the queue, it's going to go at the rear end of the queue, so it's going to be such that this 4 value here goes to the end here. And then if we remove any elements from the queue, it's going to be removed from the front of the queue as a result. So this 9 value here will be removed accordingly if we use that operation. So with queues, you have 6 methods that are always implemented regarding it. So you'll have is empty and it is full, which is basically just checking if the queue is empty, if the queue is full, because queues tend to have a fixed size. Enqueue or push, these are just different names for the push function, is where you add an element to the end of the queue. And dequeue or pop removes an element at the top of the queue as accordingly, so rear and front. And you can also have specialized peak functions, which are going to be known as front and rear, which checks what element is at the front of the queue and at the rear of the queue accordingly. Now, queues are typically used when you're implementing different types of data caches in particular. Where, let's say, if you're having data that is being streamed, you want the data to be such that whatever data was set at this point in time needs to be offloaded later on at a particular point in time in order. Otherwise, the audio comes out entirely jumbled and the video comes out entirely jumbled as well. So queues are a nice orderly way of maintaining how data is to be delivered as such. Now, there is example code provided for queues on MyLearn. So I encourage you guys to actually look at this code and see how it operates, because most of these methods here, they tend to be only like 1 or 2 lines to implement as a result. And it's very simple to go about implementing these. So it's just a matter of just watching the code and understanding how it works and just remembering which lines are responsible for which methods here. All right. Any particular questions on queues? Right, doesn't seem like there are any particular questions and queues. So, you actually have some group work here, and it's going to be advantageous to you guys if you get to start on this early when you can. The two things to attempt are actually given here on the slides. So, for the stack, I want you guys to actually have a function here named min, which will return the minimum element, and provide our reasoning for this regarding your implementation, and you need to make sure that it operates in O to the 1 time. And for your queue, instead of the queue operating such that it goes from rear to front, I want your queue to operate such that it goes from front to rear instead. Now, it's very easy to get this wrong. Remember that data flow is what's going to be important for implementing the queue in reverse order. Alright, that brings us to the end of our revision here for stacks and queues. They're basically simple data structures once you know the principle of how they operate and what methods to implement them. It's very straightforward to go about implementing each one of these. And we saw that in stacks and queues, some of the functions do share similar operations. In particular, like if we were looking at the peak function or the top element function, this is similar to returning the value at the front of the queue. And we also saw that the push and pop functions, even though for the stacks they only operate on the top element, the functionality is somewhat similar to like if we're doing a dequeue function, which is removing the element from the top of the queue or the front of the queue. So some of the code shares similar functionality between stacks and queues, but because of the nature of each one of these operate, there are also some differences as a result. All right. So before I close off our second lecture here, are there any particular questions we need to ask on stacks and queues? Feel free to ask them now. Otherwise, we'll be moving on to our last lecture for today, which is going to be linked lists. Alright, it doesn't seem like we have any questions regarding stacks and queues. Alright, let's move on to our linked list lecture. So linked list is the other simple data structure that we also need to revisit and watch its operations accordingly. Because in the past, when we did linked lists, we may not have ended up using a class implementation, we might have used a static implementation. But it's important to know how we go about implementing a linked list dynamically, because linked lists they do not have a fixed size. They can increase and decrease in size accordingly. So we need to figure out how do we go about doing these memory allocations, as well as how do we make sure that we also delete these memory allocations as a result when we need to contract our list accordingly, so forth. So that's what we're going to be looking at in this particular lecture, how to go about creating what we refer to as a dynamic linked list. Now, linked lists basically operates on nodes, and the nodes follow some sort of sequence. There are two types of linked lists, which are referred to as a single link and a double link list. Now, single link lists basically means that each node points to the next node in the linked list, so there's only one path the sequence of nodes can take. A doubly linked list means that there is bidirectional travel within your linked list. So instead of the data only going in one direction, you can actually go in two directions. So I'm going to draw what this looks like here. So for a single linked list, it comes like if we have a node here, it can only go in one forward direction as a result. But for a doubly linked list, we can have our nodes going in both directions as a result. And this is going to be important for data flow within your linked list. Now, you cannot randomly access anything in a linked list. You must iterate through each one of the nodes in order to find a particular value that you're looking for. What helps is that in a doubly linked list, because you can go forward and backwards through the nodes, this actually is a little bit more advantageous than a singly linked list. Because now, instead of, you can actually use particular sorting algorithms here if your structure of the nodes are already sorted. Sorry, you can use particular insertion algorithms if your nodes are already sorted. So the sorting algorithms that we just not learned, and we also saw in last week's lecture, can actually be applied to sort the contents of the linked list here from the lowest value node to the highest value node. And then once we have this sorted, we actually use a binary search algorithm here for a doubly linked list to find a particular value within your linked list. And because it's doubly linked, you can go forward or you can go backwards throughout the entire list as a result. In a singly linked list, because the direction is only one direction for the data flow, the advantage of this is that you don't need to have two pointers. You have one pointer, so you use less memory overall for the data flow of your entire linked list. Disadvantage is that because you're only going one direction, you can't go back in the list. So once you find something, it needs to be that you start from starting node and you go through each one of these nodes until you find what it is that you're looking for. So the explanations that's going to be provided to you here in this particular lecture is going to be focused on the singly linked list. A doubly linked list just only has one additional pointer that just reverses the directional flow of the linked list, and it's not very hard to implement. So we won't be really discussing doubly linked lists in particular. So for a singly linked list, your nodes here will have some data and then a pointer as its structure. And the pointer in your node is indicative of where it needs to go to the next particular node in the link. Note that the last node will always point to null, indicating the end of your linked list. In your doubly linked list, the nodes here will contain data and two pointers. And in this particular case, the pointers here will be towards your next node and towards your previous node. Now, one thing to note here is that note that for your start node in your list and the end node to the list, that the values of the pointers in these particular cases are going to be different, because for your start list, your starting node here, this only has this pointer here. There's no pointer pointing to something else. So you can treat this as null. And then for your end value here, for your end value or your end node, we only have this pointer here pointing to our previous node. There's no pointer pointing to your next node. So this can also be treated as null. In some particular cases, and it's also a little bit advantageous, you don't want these pointers here being the same null value. You may wish to assign them to some individual values to know that, okay, this is actually going to be the right-hand side end of the list, or this is going to be the left-hand side end of the list as a result. But that's dependent on design and implementation choices. In most generic cases, you just make sure that these pointers here are just point to null as a result. Now, in creating a singly linked list, the nodes here use a struct to define how they're actually going to be laying out their data. So we start with the struct construct in C++, and then we have our data here represented by some data type. In this particular case, we have an integer data type. It can be double, it can be string, it can be character, whatever you wish. But the next data that is going to be in our node structure must be a pointer of that same struct that we created. And this pointer is going to be indicative of which is going to be our next node to follow within our entire link. So we use the struct here to define the structure of our node, but we use a class here for our linked list to define how our nodes are linked together as a result, forming our entire link. Note here that we have two pointers of the node struct, which is going to be head and tail here. And these pointers here are going to be very important later on to indicate the start of our list and our end of our list, and how we go about expanding our lists accordingly as a result. Note that in creating our linked list here by our constructor, which has the same name as the class, once the linked list is empty, the head and tail nodes here, or the node pointers that we see here, are also empty. That's why they get assigned to null as a result. And initializing the linked list, this is the main function for doing this as a result. And in calling the linked list A here, when we create object A of type linked list, the constructor here is automatically called, creating and assigning head and tail to null as a result. So the head and tail node pointers that we just now saw here are important for tracking the first node and the last node in the entire linked list. And we're going to see that when we create our function here to add nodes into the linked list, our head and tail here are going to be affected as a result. So I'm giving you guys the code here for adding a node to the linked list. And we see here that we make use of the new construct, the pointers here for our node structures in order to create new nodes accordingly in memory. By creating a temporary node constructor and assigning data and the address bit, we can go about reassigning the flow of our linked list depending on how many nodes that we actually do have. So if our head node here was equal to null, meaning that there was no start node, we can say that this temporary node, is going to be our started node for your entire list. So you can put head and tail being the start, because there's only one node in the entire list. If it is not, on the other hand, we need to make sure that we add this node that goes towards the end of the list. So we update our tail node accordingly to represent. Because this add node function is a method in our linked list class, we call it in our main function using this syntax construct here. In traversing the linked list, remember we need to visit each node in order. So what we end up using is that we end up creating another node pointer to go about traversing the entire linked list and obtaining the contents without modifying the contents of the linked list. Now for a single linked list, when I drew that illustration, remember there's only one direction for the entire data flow of the linked list, so it goes from head to tail. In the doubly linked list, it can actually go from head to tail and tail to head as a result. So all the cases from here on forward will be for singly linked lists. So this display function is responsible for traversing the linked list, and like I said, we use a node pointer here, and we set that node pointer to the start of the list. And once this node pointer doesn't hit null, being the end node of our list, we are able to retrieve the data at the current node we are at, and we can update our temp node here to point to the next particular node, and then retrieve that data from the next node until we hit a null pointer as a result. In inserting nodes into our linked lists, there are three cases that we have to pay attention to. The first case was where we added a node to the end of the list using our add node function. But the other two cases would be where we need to add it at either the beginning of the list or between two existing nodes within the list. So let's see how we go about doing this for each one of them. So if we wish to insert a node at the beginning of our list here, and this node here is being our new node, we create the new node first, and then we need to point this new node here to the head of the existing linked list. And then we need to switch the head of the existing linked list here to point such that it starts at the new node that we created. So this comes back where we update our head and tail nodes accordingly. Right, this insertion, we're all focusing on the head node. This is why we go about doing this in this particular order. So we create the new node first. We set this pointer here for the new node to point to the existing head of the linked list. And for this new node, we switch head here to start at this new node that we created. The code for this actually is very simple. You can see basically it's only 4 lines of code that you need to put in, and this entire method just goes inside the link. And inserting a new node in between two nodes, we won't have to break the linked list and reform the links accordingly as a result. Now, this process only works if the nodes have what we refer to as unique identifiers. And that's going to be a different data field within your node structure itself. In some particular cases, you may want to treat the data field that is already existing in your node structure as the unique identifier. And once we have unique identifiers assigned to each one of these nodes, we can use the identifiers here to search for the nodes that we wish to insert our new node in between as a result. So the steps taken for this is that you need to make your traveler node similar to that of the display function that we saw earlier. And we start at the head of the list, and we check each node to find that unique identifier or data value. If we find that data value, in this particular case, we'll be inserting the new node after this found data value node. So we just then perform the following steps, so is that we create the new node, we assign the data and as such, but then we need to make sure that the pointers here match back accordingly as a result. So the pointer of the new node needs to be set that to the value of the pointer in the traveler. Because remember, the traveler here is going to be at the current node at which we were at. So just to illustrate what this looks like, let's call this our traveler. And let's say we had all these nodes here going in. So if the traveler here was at this point, and we have our new node here, call this NN, and it already initializes all our data and so forth. So because the traveler here, I'm just putting an X here, at this point, the traveler needs to make sure that this new node here grabs this pointer that exists from this particular node. And then it needs to make sure that once this new node here goes in here, and it knows its point in here, that the existing node here now points to our new node as a result. So in doing that, that makes sure that the order of the list and the traversal of the list is maintained. Now the code for this is actually given here as well, and it's just basically knowing the sequence of steps to go preserving the order of the list by inserting a new node in between two existing nodes. Similarly, additional nodes, we also have deletion of nodes from the linked list. And it's just basically just knowing how to go about doing correct order for deleting these nodes safely, and also maintaining the traversal throughout the list such that you don't break the linked list as a result. So if we had A, B, C here, where A links to B and B links to C, and if we had to delete B, we have to make sure that A now points to C, and then once this B node is isolated, we can then safely delete B as a result, maintain the order of our linked list. The general code for deleting a node here is given to you guys as here as well. And just pay attention to how the order of our instructions are given regarding how we go about separating the existing links, reforging these links, and then deleting them. Now, in this particular code, there's a problem because this does not consider if we try to delete the node at the head of the link. So, for this particular case, we're going to have to create a different method. And we can see here that the code here for just deleting the node at the head of the list is only going to be 4 lines. It's very simple. So, for linked lists, all those functionalities that we saw here is just knowing how to safely insert and delete the nodes, and how to safely add and delete them depending on the positions where they are. And you have to make sure that you always follow the order of operations in order to maintain the integrity of the linked list, such that you don't break it, as well as how to safely delete the nodes once you maintain the integrity of the linked list. And as your homework regarding linked lists, try to figure out how you can merge those two deletion methods for the nodes into one method. Alright, so that brings us to the end of our linked list lecture. Are there any particular questions regarding the content of this lecture? Alright, doesn't seem like there are any questions. So if there are any questions regarding the contents of today's lectures, feel free to leave them down in the comments below or directly email me. Regarding Wednesday's session, we may do like a quick tutorial regarding the operations of each one of these particular functions, just to see how they do operate. If not, we'll do a short review session if as required regarding any particular misconceptions that we may have regarding stacks and queues and the linked lists, or anything that we need to further explain regarding the sorting algorithms as of such. So until Wednesday, take care, be safe, and I will see you guys soon. Later.